Chapter 46, Population Ecology. So most ecological problems are associated with human population. It is estimated there are at least 6.5 billion people in the world. This also, contributes to habitat loss, and of course, man always thinking that he can change the environment in ways that will suit us, which oftentimes leads to a lot of things like, if you look here, you can see that the erosion from the human population, which carries sediment down the river, and it pours out into this body of water, forming what we call a delta. And then over here you can see some severe flooding going on due to cutting down habitats to build homes, shopping centers, all those things that don't allow for water absorption in the ground. Here's another example of something that humans have built. We can see here this dam and how we're using it for electricity, but it completely changes the habitat on the other side of this body of water. So we are very good at changing the landscape and the ecology of any environment that we tend to inhabit. So let's go back to some of the terms that we used in Chapter 1, one of which was a population. So what is a population? A population is a single type of species that occupy the same geographic area. So here we're seeing a population of zebras. There also looks like there might be some water buffalo or different type of species population that's intermingled here. So populations are influenced by resources. That would be food, habitat, place for them to actually live, environmental conditions, and boundaries, which are natural or man-made. So we can talk about how populations do affect other groups of individuals, and when these other populations interact with one another, we refer to those as communities. And communities can influence traits that will definitely allow for natural selection to occur. When we look at this deer mouse here, you can see that it blends into its environment very well, which would allow it to escape predation, specifically from snakes, which would be one of its natural predators. You also have predatory birds out in the desert habitat here. We can see the cactus sitting there. So when we're looking at the southwest area of the United States, but we also know that this interaction between different populations can be a negative and a positive effect. Like I said, if this mouse population increases, it will affect the ability for its predators to also increase their numbers because there'll be more food supply. And we're going to look at how populations are influenced, this predator influence with population size. But we also know that this little deer mouse here caused a really big scare for a while in the Southwest with a virus called the hantavirus, and how humans were dying from exposure to these particular critters that were carrying this nasty virus. And so we know that when the population of the mice went up, and drought would encourage the mice to come into people's homes, it exposed them to that hantavirus. So we, as ecologists, will look at interactions amongst these individuals within different populations to see how they influence one another. Basically, everything, abiotic and biotic, they're all related and tie into the survival of organisms on this huge biosphere. All right, so let's just review our organization. When we talk about our biological organization, we're going to start off with an individual. So that's one organism. If we have several of those organisms in the same species, we refer to that as a population. And then when we get to our community, we're talking about multiple species interacting. Generally, those are biotic factors, so everything that's alive, that's plants and animals. And then we have our ecosystem, which includes all the abiotic, which is the non-living factors, with the living factors. And then we have a biome, which is a larger area. We generally talk about our biomes as being like tundra, desert, savanna, tropical rainforest. And then all of those biomes then make up the living sphere, right? So basically the planet Earth. When we look at population characteristics, one of the things we like to focus on is density, and that is how many individuals live in a particular area. So some organisms, they are not as successful being with their density or their population numbers being high. Others require it. Then the second trait we'll look at, or characteristics here, is the dispersion, or how are they spaced in their environment. Are they clumped? Okay. Are they random? Or are they uniform? And you can see this with the picture here. Are they clumped? They're random, there's no pattern, and then nearly uniform. So they're almost evenly spaced. Generally, we end up seeing, for the most part, this clumped dispersion pattern because they're usually clumped around a food or water source. So here's some additional patterns of spacing. So we have clumped with our elephants. Again, they generally will be found around a food or water source, even and as an example with these trees. And then random, if you've noticed in your front yard, dandelions will grow anywhere and everywhere they can possibly get in, especially if your neighbors don't like to use herbicides to kill the dandelions. Now, we've talked about different biomes. I kind of mentioned some of these in a past slide. So, like, for instance, here I've got an example of a grassland and a temperate deciduous forest, which we see up here. We have a lot of, like, prairies and stuff in northern Illinois, and then we also have deciduous forest. And we know that there's kind of a transition between those two biomes, and those are referred to as an ecotone. So ecotones are where those biomes start to blend or merge and merge together, the borders there. When we look at population demographics, what's the term demographics? Demographics is the statistical study of the effects of a population. Well, as soon as we put that word statistical in, some of you guys may be cringing because that refers to a nasty little 4-letter word, math. And many of us don't like math, which is why we prefer biology to chemistry or physics. But it's not horrible here. So let's talk about this a little bit. So let's first of all, when we talk about births and immigrations with an I, that means organisms, individuals moving into a population. Those are additions. We can handle that, right? We're just going to add. And then when we talk about death or immigration with an E, exit, we're going out of the population, then we're going to have a subtraction. All right? So far, so good. So when we study population demographics, there's two things that they generally will focus on. The first one is an age structure, and that's the number of individuals at each age level. And the second is the sex ratio, and that's the numbers of females to males. So let's go ahead and talk about that first point that they're going to look at, and that is that age structure. Since each age level has a birth rate and death rate, that's going to contribute to the population change, whether it's getting bigger, whether it's getting smaller. In humans, the birth rate is greatest amongst 20 to 30-year-olds, and after 30, the birth rate drops off, so women stop having children right around 30. That's not saying they all do, but the majority of births occur, like we said, between 20 and 30 years of age. So when we're looking at age structure, we can see if we have a large population that's going into that general age group, which means we may have a population explode, which is what we had back in when we look at World War II. Once the war was over, you had this large population of individuals having children, which we refer to today as the baby boomers. And now we're seeing this huge group of baby boomers getting ready to retire. And so, again, it has a big effect on the population currently, especially when we are going to have to pay this large amount of people Social Security. We're also going to have to fill those vacancies job-wise, and we may not have the skills or the population to replace that. So it's changing the demographics or the population greatly here in the U.S. So the second topic that we look at or contributor to population demographics is the sex ratio. The number of females in a given species is the most important. The number of mature females gives a direct correlation to the number of possible births per year. So in many species, a mature male can breed with several females. So consequently, the number of males is not very significant when we look at a population increase in a certain demographic, we could say, a age bracket here. It's the number of females, because that's what's going to greatly determine whether the population's increasing or decreasing or staying the same. When we look at reproductive strategies, there's two main types. And of course, nothing ever really fits perfectly into a said category. So these again are generalizations. We have what are called K strategists, and we have what are called R strategists. So a K strategist, they produce very few young, but expend a lot of energy caring for their offspring. So they're going to put a lot of time and energy and invest in the caring and the upbringing of their offspring, and this ideally is to increase the rate of success that offspring will have, because if the mother spends a lot of time and energy forming that offspring, you could say, gives birth, and then that offspring does not survive, then the survival of that individual will end. So by investing time and energy into the care of their offspring, they're helping to ensure the survival of their line, okay, their attributes, their I don't want to say family lines, because animals don't look at it like I need to preserve my name or my heritage, but it's continuing the success of that organism. Now, our strategist goes about this totally in a different way. They will produce many young. They give very little to no parental care, and only a few offspring produce. So what we're saying is a K strategist will invest energy slowly over time, and our strategist will tend to have one big investment and hope that something grows from that big investment in the beginning. So some examples of K strategists would be, of course, primates, humans, mammals. When we look at our strategists, we're looking at, for example, insects, many plants, most plants, you could say. Again, I'm trying not to say all or none. Some others would be some invertebrates. We'll talk about some of these other examples. That's going to bring us to a topic called survivorship curves. There are three types, type 1, 2, and 3. You can see this in your book on page 1087. These curves are based on potential lifespans of different species for various age groups, expectations of when a species will die, and actually this began with life insurance, because if you're going to invest in a company that's going to provide life insurance for humans, of course, you'd like to know if this is going to make money or you're going to lose money. So like I said, there are three types of survivorship curves. There's type 1, which, if you notice here, if we look at the age, as you get older, it moves across this direction. These are the number of survivors on the side here, on your y-axis. So type 1, survivorship, so many of the individuals survive up until you get, up to probably like the 60 year mark, and then they start to slowly taper off here. So most of the individuals in a type 1 survivorship curve will survive and then die of old age. When we look at a type 2 curve, notice that it's a straight diagonal line down, which means there's really no better time in which, like your odds of dying here are the same. You could die here or here or here, and it has nothing to do with your age. And then type 3, most of the organisms die at the very beginning, but if they survive that beginning phase, they will live until an old age. A little formatting issue here, but we can work through this. So some characteristics of the type 1 curve again: long-lived, die in old age. Got that? Decline in population after later in life. Few young are produced, so generally these types of organisms are K strategists. Populations are usually close to the carrying capacity, and we're going to talk a little bit more about carrying capacity here a little bit later. So to continue on with our type 1 curve, again, these organisms are generally very specialized in their habitat. Their growth curve is an S shape. So we're going to talk a little bit about S and J population curve. So here's our carrying capacity. So this is generally the most that a specific environment will hold due to resources. So when we're talking about that type 1 curve, we notice how populations will start off slow and then they'll have this exponential phase here, but it's not quite, I don't want to say, the slope is not as steep as a J curve. So it's going to go up gradually as it approaches carrying capacity. The population growth will then slow down. It has what we call heteroparity, which is few offspring over many seasons. Will delay reproduction until mature, and again, some good examples of this are humans and elephants. When we look at characteristics of a type 2 curve, remember that the age in which an organism dies is consistent throughout all age groups, so it doesn't matter if you're young, middle-aged, or old, you still have the same chance of dying. This is generally due to high predation rates, but also these individuals do tend to produce a high number of offspring. So some examples are birds, rodents, and perennials. So here's another look at those survivorship curves. We've talked about type 1 when we were just focusing on our type 2 survivorship curve right here. This is a hydra. It's an invertebrate. So generally with type 2 survivorship curves also, we talked about like rodents and birds. They do invest some time at the beginning of their offspring's lifespan, but they don't contribute a lot of energy and nurturing. So they have their initial investment, and then the young are on their own. All right, so that finishes up our type 2 survivorship curve. All right, so with that type 3 curve, they tend to die young. So we have many hatchlings for species to survive. These are generally our R strategists. They invest a large amount of energy at one opportunity to give off many offspring, and hopefully a few will survive. So they generally tend to die early in life. Most immature species are preyed upon. They're weak, slower, inexperienced. Like I said, they produce many young. We see with fish, we'll have hundreds of eggs, and hopefully a few of them will survive being eaten. You all watch the turtles being hatched on the sandy beaches, and many of them, again, fall prey to predators. And of course we have our insects, and we could talk about the dreaded mosquitoes. Although they are bothersome, they are food for many different types of organisms. So when we look at the population of these type 3 individuals, their populations tend to be volatile. And what do we mean by volatile is that some years they may be low in population, and then you might have a population explosion. And we see that again with mosquitoes. You know, if you have a very dry spring and summer, the numbers are low, and then when you have a wet season, the mosquitoes are just terrible. These individuals tend to also be, not the mosquitoes, but these type 3 curve individuals tend to be colonizers, in that if a habitat has some kind of damage to it, and it basically, we have a clean slate, those individuals will get in there. They're opportunists. They'll get in and start growing. And we see with these individuals that they have what we call a J-shaped curve, because they will be kept at a minimal, their carrying capacity. And again, if something happens to open up that habitat or give them more food or resources, then they are going to explode out in this exponential growth here. So generally with these type 3 curve individuals, the species seldomly live more than a year or two. And I have been talking about this pesky mosquito right here. And I've also been talking about dandelions. So you could tell how I feel about mosquitoes and dandelions from this presentation. So generally they will start reproduction early. They waste little time on energy or on growth. You know, they stay small. They will lay hundreds, if not thousands, of eggs, which will, of course, then mature quickly during any environmental time period that will allow for this. And of course, we know, being up in northern Illinois, then they all die off in the wintertime, and then as soon as the weather starts getting nice again, we'll all of a sudden see that population of mosquito in full force. And of course, we have the dreaded dandelions that all of us as kids love to play with and blow these seeds and make a wish and just spread them even further. So again, they have this huge reproductive effort here. If you think about all the seeds that are in that head of that dandelion, and then they will float away and take root if the soil if they land in soil that is able to support their growth. So when we look at population growth, there's a couple variables we need to define. So if we look at the R for rate, now the rate of growth will be dependent on birth minus death. So this again, R is the overall change, B is births per year, and D is deaths per year. So if the R value is positive, all right, so if we're positive, then we know that the population is growing. If the R is negative, we know the population is getting smaller. If it is equal to 0, that means there's no growth. So we're going to see that term ZPG often, zero population growth. And that basically is, we're going to imply that the population has met its carrying capacity. So we're not going to see any growth, or hopefully not any death. But again, what could happen to that is if the environment changes over time, that carrying capacity could go down. If you look at weather conditions, drought could lower the carrying capacity because there'll be less food and water. So we can't really say that this is a long-term figure when we look at numbers and populations. Populations are fluctuating, so generally we're looking at where are things going now, and we can do a little bit of prediction in the future, but it's about as accurate as the forecast in northern Illinois. So when we look at what's called the intrinsic rate of increase, or R max, this is when we are at our maximum population growth. This is when ideal conditions exist, but as ecologists know, ideal conditions do not I don't want to say they do not exist. They do not exist for long. All right, so Rmax is generally during this period of Rmax where we would have our maximum population growth, we will see a J-shaped curve. And we do see these temporarily in an unfilled environment, but again, as those individuals reproduce, it becomes filled. So then you're going to start to slow down your growth as, again, you start reaching that carrying capacity. So we can see this in what we call a pioneer species, which is when we have we're going to talk about primary and secondary successors. Primary is generally when you have brand new habitat for the first time exposed, which does not happen often. Or we have a catastrophic event, which is what we would call secondary succession. And this could be after a forest fire or a volcanic eruption, a hurricane. So this is when the current habitat is destroyed and now we have, again, a clean slate in that area, and individuals are able to go in and occupy that space. And again, this population growth is generally it's temporary until they have filled all the available resources that they could possibly maintain that population. So here's just another graph showing you the comparison of exponential growth curve. That would be our J curve right here versus our S or sigmoid growth. Now notice at first these are both exponential here. The J shape just continues with that exponential growth, as this one tends to be more referred to as logarithmic. And then once it reaches that carrying capacity, it will slow down until it reaches Z, P, G. So we look at exponential growth again. We're going to assume that we have unlimited resources, which, like I said, never happens over a long period of time. We also have been talking about carrying capacity. So here's where I'm actually defining that, where K is the variable we're going to use. That's the letter we're going to use to represent carrying capacity. And that's, again, the maximum population size that a particular ecosystem can support. When we talk about carrying capacity, we're looking at food, water, living space. You actually have to have a place to occupy. So these are things that we take into consideration with carrying capacity. So when looking at other things that are going to affect the carrying capacity, one of the things we will look at is density dependent factors. Does a population's number, so if there are more individuals, if there's more density of individuals, does it have a direct impact on a population? Now we know with more individuals, you're going to increase competition. It's going to affect predation. It's also going to affect parasitism. And when we talk about parasitism, a perfect example I like to use is think about when you're home during the summer, and many of us rarely get sick. But as soon as we go back to school and we have 1,000 students in a building, we're in a close proximity to one another, and now we're passing germs back and forth. So as the density of humans increase in that location, the more illness we are going to see. We're also going to see more competition for food, for water, for space, okay, for Wi-Fi. I mean, we could relate this to all kinds of normal things that we deal with on a daily situation. All right, as we know, teenagers are having a harder time with jobs because the teenage jobs are being taken because of population increase and lack of higher paying jobs. And so we have adults that don't have jobs, and so they're taking teenage jobs. Again, all these things are density dependent factors. Now the other type of environmental condition you can say here, or environmental resistance, or how carrying capacity is affected, is density independent factors. Now this indirectly is an effect on a population. So it doesn't matter if there are 1 million people living in McHenry, we're still going to have an 18-degree for a high today versus if there were only 1,000 people in McHenry. So the population has no effect on weather. What about floods and droughts? Well, we may contribute with our building to having excess runoff, yes, but we really don't affect how much rain we get in a year, or whether we don't get any rain and it's a drought. Fires. All right, so in general, we're not going to have more forest fires because there's more people. Now, we can say that we could increase the number of forest fires because we have people who are careless and start them, but in general, naturally occurring forest fires and stuff like that aren't going to be increase or decrease based on our population. And of course, habitat destruction. And again, that has to do with like earthquakes or, those types of things. Because, we could say that habitat destruction would also be a density dependent factor, because humans are, as our population is increasing, we need more space and we are destroying other organisms' habitat. So you can kind of look at that in two ways when you talk about habitat destruction. So this just is going a little bit further into our S-shaped curve, and we call that the logistic growth curve. Carrying capacity, so our K has been reached, therefore our rate of population increases 0, so our births are equaling our deaths. So when we talked about that, we kind of start off growing, and then it starts to level out where R equals 0, or ZPG is reached, because we've reached that carrying capacity. So when we talk about our logistic growth model, you could say here, it works very well with small populations that are in equilibrium. It does not take into account random chance. So we'll talk about random chance in more detail when we get to evolution. So these are called population growth curves, and you do need to know how to read these. They may have this on the AP test. Now, notice we were talking about the significance of males versus females. So if we look at Sweden and its population, so again, we have our ages here. When we're looking at, is a population growing? Then we want to kind of focus in on, you can see the blue area here. This is generally when females will reproduce. All right, so we want to look and see. Now, we could say for Sweden that it's kind of stayed very constant. You don't see a whole lot of shape. It's almost a straight line. So they have a very stable population. If we look at Mexico now, this is a problem. This is very problematic, because you notice here we have this, basically this, I don't want to say bell-shaped or upside-down bell, or it would be actually a right side of bell, or Y. But it's getting fatter at the base, which means your population is getting bigger. And it's getting bigger pretty quickly. So this is a population that is growing. Now, with the United States, now, if you notice, we have up here, this was our baby boomers, and then these are the kids of the baby boomers. But notice here, we're kind of getting smaller. So we're stabilizing, and the United States is actually becoming a more stable population, and will probably start to mimic Sweden over time. And that is what we are finding with most technologically advanced populations, countries, that they require a lot of resources and energy to raise their young. Therefore, the number of offspring that they are producing are fewer and fewer, and this is helping to stabilize the population. So when you look at different countries, and not to pick on Mexico or whatever, because if you look at some of the populations in Africa, they're going to resemble this, but this is contributing to the fear that we are reaching our planet's carrying capacity. And when we see these populations still growing exponentially in some areas, it's very concerning for ecologists. So these are things that we're going to look at when you look at, human population or other organisms' populations. We also know that different areas have different carrying capacity. You could say like the U.S. has a lot more resources just because of its climate, its growing potential, versus Africa, which they don't have the ability to produce the large amount of food that we do based on weather and habitats resources. So even though their population is growing, their carrying capacity is in those regions maybe much lower than, let's say, the US or Europe. So these are all things that, population ecologists will look at when studying human populations. Now, to add to what I've already mentioned, I know I'm going on and on about these curves, but do pay attention to the elderly here. Notice that in Sweden, many of their elderly, they live quite a long time. It's pretty stable up there versus how small it is here in Mexico. So their senior citizen communities are much smaller. And also look at the United States. This is a problem when you're talking about Social Security. It's also very interesting to notice how the females, there are more elderly females than males. Although we are going to start seeing this trend be more symmetrical as people move up in the age structure, and both women and men, because women are now working now. So we should see a shift here in the females basically dying off sooner than they have their predecessors have. So these are all things that are really important to look at when you look at populations. And this concludes the lesson for chapter 46. Hopefully you will have this all done before we get back from break. And if you do, you can start your homework or start reading chapter 47.